Here I have two Softrock Ensemble transceivers. This one is completely in its original shape. I haven't changed anything in it. And this one is modified in several ways, but for this video at this point the only relevant modification is that the gain of the receive op-amps is reduced. I have replaced the 4.99 kilo ohm resistors with 1.8 kilo ohm and increased the feedback capacitor correspondingly. That means the gain is about 7 dB lower on this unit. Both of the units are connected to Delta 44 sound cards in two different computers. This one, which is in the original shape, is connected to a Delta 44 which is also in its original shape with no modifications. This one with lower gain is connected to a Delta 44 with a lower noise floor. It is modified as described on my home page. You can see one of the modified boards here. But there is one more modification. These resistors here that make the sensitivity the same as the original unmodified board, they are 6.8 kilo ohms. I have connected 1.4 kilo ohm in parallel with each one of them to allow to set the most insensitive setting and still get the saturation point close to the saturation of the op-amp in the Softrock. So the card sitting in the computer now connected to the modified Softrock is adapted to the Softrock in its modified state. Both units are fed from this hybrid here. Here is one signal coming directly from a signal generator, and here is the other signal which is sent through a 10 megahertz notch filter. And there is an attenuator on the output of the filter that is to provide better isolation on the notch frequency, better isolation between the Softrocks. This generator is centered in the notch, and I have set it to minus 97 dBm, which means that the signal entering the two Softrocks is minus 100 dBm. Here is the screen of the unmodified system. I have set gain in consumer mode because that is where performance becomes best when units are in their original shape. And you can see the signal from the generator, and I have calibrated the S meter to show minus 100. And I can switch off the generator, and we can see that the noise floor is at about minus 121. And here is the modified system. It's also set to minus 100, and the noise floor is also minus 121 when the generator was switched off. Both systems are set for a bandwidth of 2 kilohertz. After expanding the S-meter scale a bit and using the readout function, I find that the noise floor is actually minus 122. And it is very similar on the modified system, minus 122. That is at a bandwidth of 2 kilohertz, means 33 dB, so it is minus 155 dBm per hertz. That's 19 dB above room temperature at minus 174, so the noise figure is 19 dB, and that is perfectly fine for a frequency of 10 megahertz. I have now added a strong signal a couple of kilohertz below the notch frequency, and you can see glitches in the sound card become very visible when they occur occasionally. There's something wrong with this system. I don't know what it is. It's Windows XP, and it has traditionally worked well with the Delta 44, but it doesn't really do that anymore. Probably I have installed something that I shouldn't have installed on this computer. Anyway, the strong signal is this one. It's at -7 dBm. And I can see, if I press A, that we are 3 dB from saturation of the Delta 44. But if I bring up the signal by a single dB, you can see here that the desired signal, the one in the filter passband, becomes weaker, and you can also see there is a rise in the noise floor. So at this point the op-amps in the Softrock are saturated. So 7 dB, that means -10 dBm is the strongest signal that the Softrock can take in its original shape. The modified unit, I go up in steps of 1 dB. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, here, 9, and I can look at the margin, 0.86 dB, and now it's saturated. It means the Delta 44 is saturated, and it's very close to where the Softrock is also saturated. And I back off 1 dB more, and you see no dramatic difference anywhere. Not up here and not here. And this level is +2 dBm. Means that the signal into the Softrocks is -1. So it is an advantage of 9 decibels. And that's not bad if it were true, but it really isn't, because there are other problems with the Softrock, and that is reciprocal mixing. This computer works okay. There are no glitches on the Delta 44, while on this one there are occasional glitches. That's not what I'm going to try to understand at this time. Some other time perhaps. I switch off the signal -100 dB on the center of the notch, like that, and then switch on, well, it is already switched on, a strong signal, very close to saturation of the original shape Softrock, and it's now 5 kilohertz below the notch. And I step it downwards in steps of 5 kilohertz. Well, before that I switch it off, because that will give reciprocal mixing. Remember, we had -122, now it's -120. And you can see there is 2 dB. And it's, well, similar, just a little less here. And I switch back the generator. So reciprocal mixing at the close range is not a problem. Not much of a problem anyway. And I step now downwards in steps of 5 kilohertz. Looking at the noise floor. Well, here is a spur. And we can see the noise is going up. And now it's going down again. So about here, the signal is outside the visible range. It is about, what is it, 40 kilohertz away. 45. And if I switch off the generator, you can see reciprocal mixing is, well, I can measure it. The noise floor is minus 122.2, and with the signal on, it is 119.6, 22.2 to 19.6, that is 2.5 dB or something. Not horrible, but it will limit the possibility of doing improvements. Now I increased the level by 9 dB, like that, and this one is not saturated, but when I switch off the generator, you can see the noise floor goes up by, is it 4 dB or so? So reciprocal mixing is somewhat a problem at close range. And I step the frequency downwards. Looking at the noise floor, and it improves. That's normal. Larger distances in frequency, less noise. But now it increases again. And more, and even more. No, this is a spur. Well, there seems to be a maximum. I step in the finer steps to avoid the spur. So there is a maximum in reciprocal mixing at about this frequency. Is it about 50 kilohertz below the desired frequency? And I switch off the generator. Oops. There. And look, how much is the noise? It's from here, minus 116 to minus 122. That's 6 decibels of reciprocal mixing. So the improvement wasn't 9 dB, it was much less. The local oscillator is powered by the USB cable, so it's enough to have USB connected to make it run. I have put one turn on this T1 transformer to extract the signal, and I have sent that into a PerSips. And this is what we can see on the PerSips screen. We have noise sidebands. If I switch off the signal, or just disconnecting here, you can see there is also wideband noise. This is now 28 megahertz, and I have set the oscillator to 7 megahertz because it runs on the 4th overtone. Anyway, this looks like USB, and I guess this is the reason for the reciprocal mixing problem. One thing I can do is to decouple this chip better. I put the capacitor across here. Not so easy to hold it while holding the camera. You can see it made some rather big difference. And I remove it again. And I happened to short something, so the frequency changed. It's easy to modify the chip. I happen to have 150 nanofarads that would fit for this purpose. And here is the result. The USB noise seems to be gone, but we have the normal noise that it strongest close to the carrier, and that drops off gradually. I disconnect the signal, and you can see where the noise floor. It's on the third level in this spectrum, and it's 10 dB per division. So the noise is 10 dB up here and not visible out here, and this Perseus is running very close to saturation, so this is now a very clean signal. And now I put the unit back into service. The noise floor is as before at -122, and I switch on the strong signal at the worst position. And you see there is still reciprocal mixing, and I think the level is the same as it was before. (116 to 122). That's 6 dB. I don't know the reason. The measurement I did with the Perseus was at 28 megahertz, means while tuning at 7 megahertz. Now I'm tuning to 10 megahertz, and things could be a little bit different. Anyway, it hasn't become worse, and the oscillator is cleaner on 7 megahertz at least. I have now replaced the notch filter by a not very good notch on 7 megahertz. And the signal at the center of the notch is still at -100 dBm. I had to change the calibration a little bit because the response is not perfectly flat on the Softrock. And it's the same here on the modified unit. I have connected an antenna. It is a dipole for 20 meters, so it's not a good antenna, but I have preamplifiers in front of it, so I can be sure that the noise we see on the sides here is from the antenna, so it represents the actual noise temperature at 7 megahertz. And of course the same in both systems. Now I increase the antenna signal, and you can see we have occasional problems, pops and things, and it's the same. The modified unit is no better than the one in the original shape. At first that is surprising, but on the second thought it is not. I have put now a bandpass filter in front of the notch filter to limit the frequency response to about half a megahertz, around 7 megahertz. And this is the original Softrock, and here is the modified one, and you can see there is a dramatic difference. I can attenuate by 10 dB, and of course signal levels change. Something that was causing this intermodulation has just disappeared. I turn up the level instead by, well, this was maximum. I have to turn up on this stick, like that. So this is the original shape Softrock, and I switch to the other one. And of course it's difficult to judge, but you can see the S meter here. It is around minus 115, and here it is around minus 85 or minus 90. So the interference level is much higher. If I switch on the signal at the passband center, we can hear it quite well here. And if I switch off there and switch on here, we don't hear it anymore. I switch it off and on. Well, you could hear it very weakly. That's because the QRM became weaker. So the problem with the Softrock, when it doesn't have any selectivity in front of it, is not the saturation of the op-amp or the sound card. It's the mixer, probably. It could be switching diodes or something, but it's wideband side that saturates. So if you don't have a filter, there is no reason to do any other modification. Here you can see the properties of the filter. It's not sharp at all. It's about 1.5 megahertz wide. I made it long ago for some different purpose. And you can see the markers. It's marker. It goes from 6.5 up to 8 megahertz between the 3 dB points. And matching is not particularly good. Nevertheless, it removes enough of the wideband impulses to demonstrate that the modifications really make some significant difference between the units. So maybe it would be a good idea to try to find why there is a peak in reciprocal mixing at 50 kilohertz. It isn't the oscillator, most probably. The USB interference leaks into the receive side other ways, and maybe that can be prevented somehow. I have set this generator 9.95. That's the worst frequency for reciprocal mixing on the modified unit, and probably on the unmodified as well, but there it's not very visible. And this is what I see on the S meter. I switch off the signal. Like that. And you can see the noise floor is a bit below minus 122. And I switch it on again. You see how it looks here with the presence of the noise and how strong it is. There is, however, something I can do about it. I do like this. And it's almost gone. What I do is to connect 470 microfarads from the ground point of T1 to plus 5 on R14. Like that. And it has this effect. Very interesting. So I solder it in place. So this is what I got. Reciprocal mixing is about 2 decibels at the frequency that was worst before. The strong signal is now 10 kilohertz below the selected frequency, and I will check how reciprocal mixing changes when I step the frequency away from here. At this point we have, what can it be, 5 dB, 6 dB, but it's only 10 kilohertz away. And I step downwards, and you see it reduces fairly rapidly, and now not so rapidly anymore. But it goes slowly downwards. Now I'm 200 kilohertz below the selected frequency, and I switch off the strong signal. And you can see it's still about 2 dB. And I go another 100 kilohertz downwards, and one more, and one more. So it seems this is the flat noise floor of the SI570. Now I'm 1 megahertz below, and switch off the strong signal. And here reciprocal mixing is about 1 dB. So reciprocal mixing is coming, and probably unavoidable, because I think this is the limit of the SI570. So it's not meaningful to add a better RF filter and bring down the gain of the op-amp a little. I could do that because a noise figure is a little bit better than necessary. We can see that. I switch off the strong signal. Now there is nothing, and I disconnect the power supply to the unit. And you could see, well, maybe. I will read it out. Now the noise floor is minus 124, and I put back the power. And now it's minus 123. Well, it wouldn't be a good idea to reduce the gain any further below this. There is one more thing I have to do, because the modified Delta 44 puts an impedance of about 1 kilo ohm here, while the Delta 44 is 10 kilo ohms. It means that this capacitor C75 as well as the other one C74, they are far too small, so I have to increase them. And I want them to have a lower corner frequency than they had in the original shape, so I will make them 10 microfarads. As it happens, I found this. It's tantalum electrolytics, 100 microfarads, 10 volts, and they are small, so they fit here on the board. I'm not a video specialist, as you might have noticed. Anyway, this one and that one. Now the low frequency response will be fine. For Linrad, the lower the frequency, the lower frequencies we can get through, the better, because it improves calibration. The DC blocking creates a notch at the center, and Linrad has to guess what the phase response across that notch is, and the narrower the better. I have now added a 1-to-3 hybrid and connected a pair source together with the two Softrocks. so I can compare these three receivers. I'm using the 10 MHz notch filter for that. And here is the Perseus screen. You can see the leak through from the Softrocks here. They are not on exactly the same frequency. The signal here is from the signal generator. I have set it to show -100 dBm. And I have done the same in the original shape Softrock here, as well as in the modified unit here. Here you can read 100.0. And I switch off the signal generator and have to wait for a while to see where the noise floor is going. -121.8 for the Perseus. And I have to look here. -122. That is very similar. And here -123.3. So this has a noise figure that is 1 dB better. 1.3 actually. So to make the comparison fair, I add a 1 dB attenuator here. With 1 dB attenuation, I of course had to change the calibration here, and then I switch off the signal generator to see if I come closer to 122. (122.2). That is half a dB better than the Perseus. So I don't care about half a dB in this test. Note that the bandwidth is 2 kHz, fairly accurately here, here, as well as here. So it is okay to do the comparison this way. I have now switched on a strong signal, about 10 kHz below the notch. And I look at the S-meter here, 119. And I look at the Perseus, -121. So I have reciprocal mixing in the Softrock, not so much in the Perseus. And I continue upwards with the signal level, 1 dB, 2 dB. Now I got a lot of extra things in the Perseus, 3 dB, 4 dB, 5. Here it clips. So those extra things probably come from the Softrocks that go into saturation. So the Perseus goes into saturation at +12 on the generator. While the Softrock goes into saturation at +10. So it's okay at 9. So there is a 3 dB difference in the point of saturation at close range, but there is 2 dB of reciprocal mixing. So the Softrock is about 5 dB below the Perseus at close range when we look at noise and saturation, the blocking problems. The original shape Softrock is of course heavily saturated. I have to bring the signal down. And I have this problem with glitches on this computer. Up 1 dB, well, 2 dB, that saturates. So here is the level I can reach, and I look at the noise floor. Oops, I have to avoid the glitches, which isn't so easy, because they come so frequently. Here, minus 117, and I switch off the strong signal, and you can see there is more reciprocal mixing in the unmodified, and that happens at a much lower level, +2 here, and I don't remember where the modified unit was, but it's considerably higher. What matters is, of course, performance on a real antenna. And you can see here the perceivs is clipping occasionally. So this is the limit for how far I can go. I'm using a 20-meter dipole now. I have this attenuator and it's set to 0 for the perceivs to go into clipping. This is too much signal for the modified Softrock. I turn down the level in 1 dB steps. And you can see how the noise floor goes down. And I go for a 10 dB step and go up again in 1 dB steps to see. Well, I switch off the test signal, and now I turn down the antenna signal quite a lot. So this is the normal noise floor at minus 122, and I turn up for a 3 dB increase. It's something like this. And that happens at 28 dB on the attenuator. And the noise floor in the unmodified Softrock is very similar, minus 116, and this is perhaps minus 117. Means we have a wide open front end in the Softrocks, and they receive, I don't know exactly what is the source of problems, but it could even be medium wave. It's now in the middle of the night. The perceivs has some selectivity on the input, so maybe that's why it is better protected. Here is a filter for 14 megahertz. It's about 300 or 350 kilohertz wide at the 3 dB points. I will change the notch filter to 1 on 14 megahertz and see how the receivers compare when there is adequate filtering on the front end. The Softrock units cause interference to each other. I have now placed them with the LO at nearly the same frequency. I can step in steps of 100 Hz by clicking the arrow here. And you can see how the interference from one Softrock to another behaves. And on the perceivs, you cannot yet see that there are two different frequencies. Here is one of the Softrocks and here is the other. Well, I continue to separate, and you can see on the perceivs now they are on two different frequencies. And when they are far enough apart, the interferences come outside the screen. So I go back to place them on the same frequency. as close as I come with this 100 Hz stepping. This is not going to disturb the measurement I want to do. I have added 10 dB of attenuation in each receiver to reduce the interference from one Softrock to the other, and of course also to reduce the signal levels they send into the perceives. And the perceives also of course has its own attenuator. The test signal is then of course at minus 110 dB because of the 10 dB attenuation, and it's the same of course in the perceives and in the modified Softrock. And I will now turn on the antenna signal through the about 350 kHz wide bandpass filter. And now I'm listening to the perceives. You can see it's doing ADC clippings occasionally. Not very often, but now and then. And I have the amplifiers here and an attenuator, so I can set a suitable level for the perceives to start clipping when these attenuators show 0. So that's the position I'm at now. And I'm listening still to the perceives. And you can see there were some clippings. So I stop the perceives like that and listen to the modified Softrock. And place the signal at the center, the test signal. I switched it off and I switch it on again. You can hear it, but it's a lot of interference. But 10 dB attenuation. And now there is a little interference, but not much. Some little interference in the background now and then. The original shaped Softrock has severe problems occasionally. You can see in the waterfall or in the S-meter. But this one is fairly okay. And there could be signals on the mirror image, so it's more clear. I increase by 5 dB. And now it's clear we have interference from nonlinearities, but the original shaped Softrock has a big problem. It needs another 10 dB attenuation, like that. So, on antenna signals, when the frequency range is limited, show about the, was it 9 dB improvement that the narrowband lab measurement indicates. With 20 dB of attenuation here, and with the original shaped Softrock and the original Delta 44, we have the glitches, but otherwise there is no nonlinearities or no interference. There is a little bit from the mirror image. And now I switch off the test tone. And you can see the noise floor is here. I can read it out. Minus 123 dB. Then I click at the noise floor from the antenna signal here. And that is 88 dB. So from 88 to 123, there is a 35 dB headroom, and we do want the noise floor to increase by 5 dB when connecting the antenna. So with this original shape receiver system, a 30 dB weaker signal from the antenna would be appropriate. So that's about the gain I have applied to force it into nonlinearity. And the modified unit then is of course about 10 dB better. Now I'm talking about, I think it was 9 or so. So when this extreme dynamic range are useful, that is when you have another station on the same band operating maybe in a field day or something. So there is one very strong signal pretty close. Then the 10 extra decibels would become valuable. Otherwise, it doesn't matter. I made the test signal 10 dB stronger, so it's at minus 100 dBm. And you see now there are ADC clips fairly frequently. I'm listening on the modified Softrock, and you can hear the test signal. And I switch it off and on. Off, on. And the level is approximately the same as the level of the interference. But we have heavy clipping now, so I can attenuate a little to have clipping less intensive, and then we can hear the test signal quite well. Now it's not clipping anymore, and the test signal is fairly strong. Could be copied, even though there are clippings occasionally here. But if I go for the original shaped unit here, and I go on and off with the test signal, doesn't matter. Well, it is at minus 100 and the interference is 20 dB stronger. So I need the 10 dB attenuation. Now, and then the test signal, and we can hear it very well, of course. But there is no clipping on the Perseus, of course. The 10 dB. Well, we can hear it a little bit. So of course interference changes all the time, but there is a big difference on the waterfall here and on the waterfall here.